the trig graph of a sine of x. So it doesn't tell us necessarily what interval to graph them on. Sine of x just kind of goes on infinitely in both directions. Since they're asking for the limit as you approach pi over 2, we want to make sure that pi over 2 is covered on our graph. So I think it probably makes sense just to do the positive side of the sine graph. There's no need to overwork ourselves and go in the negative direction. But just as a quick review, a sine graph starts on the midline and ends on the midline. It can look like that, a sine cycle, or it can go down first and then up, but it still starts on the midline, ends on the midline, yes? This one's a positive sine, this one's a negative sine. So this is just really the parent graph. It's a positive sine, but how long is the period? How long does it take to complete one cycle? 2 pi, very good. So if I just, and anytime you do a cycle, you want to scale it out so that your number of units that you make the full cycle can be divided into 4 parts, kind of like the 4 quadrants. Does that make sense? So I'm either going to let 2 pi be 4 units out, or 8 units out, or 12 units out, something that's divisible nicely by 4. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We'll just really extend it out. So my cycle's going to start at 0 and end way over here at 2 pi. So I'm just going to label that 2 pi and this 0. And really what I have here is my cycle's going to start on the midline there and end on the midline way over at 2 pi. So there's the midline starting point and the midline ending point. The reason I like counting by something that's divisible by 4 is because we have to find the halfway point to get in the middle here. If you look up at the graph, you have to find the halfway point once, and then you have to find those halfway points of the halfway point, which is essentially dividing it into fourths. That's why I picked that number to be divided by 4. So if this was 12 units long, I'm going to go out 6. 1, 2, 3, 4, 5, 6. And that will be pi. And that's where this middle point is, still on the midline. And then what's our amplitude of the parent graph? 1. Now, I could count by ones and really squeeze that in there, or I could just make it scaled so 1 is like up 2 units. And so if 0 and pi are 6 units apart, then halfway in between those would be 3 units in. We're going to hit our maximum at 1. So on your basic parent graph over here, that's like going halfway in between the first 2 midline hits and going up your amplitude. And then between your second 2 midline hits, we have to go halfway between and go down. So again, 3 more units and go down to -1. Good? So if we now want to look at the limit as we approach pi over 2, first of all, where is pi over 2? In between what, Maya? 0 and pi. So it's where we have that maximum. Pi over 2 would be there. So as we approach, so this is where we focus in on the graph, because that's the limit that we're approaching. As we approach from the left, what number are we approaching? 1. As we approach from the right, what number are we approaching? 1. Do they match? Yes, so that's your overall limit. See how this one didn't have a superscript? So it was asking for the overall limit, which you still analyze from the left and from the right, but you can only answer if they match, which they did, and that was 1. So if they didn't match, we would say does not exist. Good? Okay. So that's just maybe graphing a trig, so remembering how to graph trig functions. Piecewise functions. So here's something that's essentially a linear graph everywhere, but except for when x is 3. Right at 3, we have a point at 3, -5. So I'm going to graph the line 2x minus 4, just using my y equals mx plus b knowledge. So this is starting at a y-intercept of -4 and going up 2 over 1, up 2 over 1, up 2 over 1. So right now, my line is existing everywhere. The piecewise function says, though, we want it everywhere except for when x is 3. So right when x is 3, 1, 2, 3, right here, I need to put an open circle. Because the point when x is 3 is not actually on the line. Instead, when x is 3, this is where our second piece comes in. When x is 3, what's my y-coordinate supposed to be? -5. So it's just a removed point at -5. So open circle here, closed circle here. And that ensures that it passes the vertical line test still, so it's still a function. If you close this and close this, you would fail the vertical line test there. Okay? So now, to answer the question, what is the limit as we approach 3? 3 being right here, we're focusing in here. As you come at 3 from the left, you're tracing this. What is the y value approaching as you approach 3 from the left? 2. What is it approaching as you get to 3 coming from the right? 2. Do those match? Yes. So the limit still equals 2. Even though the function value is not 2, the limit is. Do we follow that? This is called a removable discontinuity. So if you see that word removable, that really just means a hole. There's holes, there are jumps, there are asymptotes. All those are reasons why a graph might not be continuous. And this graph is not continuous because if I'm tracing it, I have to pick my pencil up off the paper, and as soon as you have to do that, you lost your continuity. But it's removable because it's just one point shy of it. Versus other graphs we'll see, like something like this. If I'm tracing this graph, I also have to pick up my pencil off the paper right there. So it's discontinuous right here, but this one's not removable because I can't just insert one point to make it all better. Does that make sense? But here, I could just put my pen, like insert one point. If you have the freedom of inserting one point, if that would make it all better, then it's considered removable. Anything else is considered non-removable. Like I couldn't pick one point that would just make this all mesh together. Okie doke? The removable, how about, let's go back. Do you follow what continuous means? Okay, I'll go back to that. Continuous means that you can trace along the graph the entire time without any interruption. So in this image here, do you see how there's an interruption? I have to pick my pencil up off the paper and I have to go back down and start over. Here, there's no interruption. This is continuous everywhere because this graph will just go on and on. I never have to pick my pencil up off the paper. No, I'm not really. I'm beyond limit right now. I'm talking about whether continuous or not. So, is it the limit part that you're confused on? Okay. So if I go back to the limit, it's when I trace towards that value coming from the left and from the right, what is the graph, what point is the graph approaching? So this one, looking for your limit as you approach pi over 2. If I go from the left and from the right, Ryan, and my two fingers are pointing at each other, then the limit exists. And it's whatever that y value is, which is 1. So on this one, as I come at 3 from the left and from the right, my fingers are also pointing at each other. And so you take that y value. Versus something like this, if I go from the left versus from the right, my fingers are not pointing at each other. So that one would not have a limit that exists. Okay. Okay. All right, so down at the bottom, another piecewise function. We want to graph this parabola anytime x is less than 2. So this graph is going to go up until 2, but not including 2. So it's going to be 2 with an open circle, essentially. So the end point is 2 comma 9. Andrew says we trust him. He just plugged in 2. 2 squared is 4. 4 plus 5 is 9. It's an open endpoint at 2, 9, which, trying to think the best place to put my, all right, well, I'm gonna, 2, 9 is pretty up there in the first quadrant, so I just made my x-axis far down so I could count up to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then there's a couple ways you could do this. You could graph the parabola that gets shifted up 5 units and then just erase the half that you don't want. Or you could just steal points from your graphing calculator. So if I were to want to find points, well, you could plug them in yourself. This is when x is less than 2. So right at 2, it's an open point. If I plug in 1, what do I get? What's 1 squared plus 5? 6. If I plug in 0, I get 5. If I plug in negative 1, I get 6. If I plug in negative 2, I get 9. So this graph, I only see the portion of it that's less than 2. Any questions on that? And then once I equal 2, and then on the higher side of 2, I have a closed endpoint at 2 comma what? I haven't graphed it yet. Because I graphed the parabola every place less than 2. Here's 2. I graph the parabola every place less than it. And then the next one is going to be greater than an x of 2. Follow? Gotcha. So this closed endpoint is at 2 comma what? 7. And then you could plug in a 3 and a 4 and a 5 and a 6 and get numbers. Or you could use your knowledge of lines and how they work. The slope is up 3 over 1, right? So however you do it, I don't really care. You can just see that the rest of your graph is going to look like that. So when we are looking at 2, now it's a little bit more split up because it matters a little bit more. If I'm approaching 2 from the left, that's from numbers smaller than 2, which is the first piece, which is gave us a y-coordinate of 9, right? And you can look at your graph now. If I'm approaching 2, so you're focusing in here, from the left, my y-coordinate is pushing 9. It never actually reaches 9, but that's the limitation it's pushing. So this equals 9 if you're coming at 2 from the left. If you're coming at 2 from the right, you're using the second interval. Number's bigger than 2. If you're coming at that, your y-coordinate is a pushing, and actually gets to it this time, 7. And do they match? No. So the overall limit does not exist. And on top of it, to go that next step to talk about continuity, is the graph continuous at 2? No, right? We have to pick our pencil up off the paper. Could we fix it just by inserting 1 point? No. So it's also non-removable. You could insert a section, like a little smooth line, right? But that's not a point. Also, if I did connect these with a smooth line, all of a sudden this wouldn't be a function anymore, because it would have to be a straight vertical line and it would fail the vertical line test. Follow that? Okay. I think that's it. Yes, you're doing all of them.